Okay, so let's consider like a stretched rope or string or something, and we pluck it at one spot. So we move one end up and down or something. So what happens is that pulls a tension up, which pulls up this part. This part pulls down there, and so you end up with a wave traveling down here at some speed c. And so what we want to do is figure out the speed of a traveling wave. And so to do that, we look at this thing and we get this wave and it's traveling along. And we think about it and we say, well, what's causing it to do that? Well, we've got a tension here. I'll use F for the tension instead of of T, because we're using T for period. Now that tension is pulling down here, which is what's pulling this down. Okay, but because this was going up, then it's pulling up here. So, but the tension pulls it back down, and so that's why the wave would move. Well, if you're standing here as the wave goes by, then you see one little piece go up, and then it comes back down. Okay. If we have a harmonic wave, in other words, if you're moving this end up here up and down harmonically, then we have harmonic waves moving. And so as the harmonic wave is moving, each little piece goes up and down in harmonic motion. Okay. Now this is our clue. Harmonic motion, going up and down in harmonic motion, we realize you can think of it as just one component of circular motion. So if you look at a wave up here, one little piece of the one little piece of the wave material goes up and down. So it's down here, it's part way up here, it's all the way up here, down here, and so forth. So as the wave moves, all these little pieces go up and down. So it's as if they're in a piece of harmonic motion. Well, moving harmonic motion, if harmonic motion is kind of like rotational motion, moving harmonic motion is going to be like rolling motion. So in rolling motion, we have circular motion. So we can think of this as at the top of this wave up here. Now, assuming that the amplitude is kind of small. Now, if the amplitude is really big, then what I'm about to say doesn't really hold. But assuming the amplitude is reasonably small, we can approximate mathematically at the top of this like rolling motion. And so that means that there's going to be a centripetal force here. So the centripetal force, we know that centripetal force equals mv squared over r. Well, what v? That's the v of moving. Well, we know that the rotational v and the linear v in rolling motion is the same. So that means this v is going to be the wave speed c. So this will be mc squared over r. Okay. Now, those of you that are a little bit into physics, that immediately like catches your attention here, because, even though we're not talking about the speed of light here, the speed of a wave, all of a sudden we do have this mc squared in here, which plays a major role at the very end of physics 2. Okay, and except in that case, then it is the speed of light. And so, but again, that also relativity also comes from the wave nature of light. And so we'll get to that into physics 2. Okay, so we got this centripetal force, and we say, what's causing the centripetal force? Well, we're pulling down on it here and here. Okay, so if we imagine some little piece at the top of the wave up here, there's our mass m. Okay, so it's going to be some piece at the top of the wave, and so on one side we're down some distance theta, down to here's theta. So the total downward force is going to be F sine theta to F sine theta. So that means we could then say that 2F sine theta equals mc squared over r. Okay. Well, what about that M? That's the M at the top of that wave. So that's going to be the M in this little piece of material. So as this was up here, again, that's the little M that was right there. Okay, and so it was some angle theta this way, some angle theta that way. That's why the tangents were each tilted down some angle theta. Okay, so that means the angle from one side to the other is 2 theta. And I want to know how much mass is that. Well, it's proportionate to the total mass. Okay, so if the entire string has some length L and has some total mass M, if I want to know the mass in this little piece that's length X, then X is to L what little m is to big M. So I could say that little m is big M over L times X. Now, mass per volume is density. But I can define something mass per length and give that a different letter, mu. That is going to be the linear mass density. So m equals mu x. So mu, the linear mass density, is the mass per length of the string. And so that means that if you have double the length, you have double the mass. So, but how much mass is in here at the top here? Well, remember I said this was as if it's part of a circle, and this was 2 theta. Well, x, the distance there, is going to be r times 2 theta. Okay. So 2f sine theta, total force down, is the centripetal force mv squared over r. So we said that the m is going to be the mu times the x, so c squared over r. And so the x was going to be the angle 2 theta r c squared over r. So the r's cancel, the 2's cancel. So f sine theta is mu theta c squared. Now, as long as we're only talking it near the top of that circle, then we can make the small angle approximation that sine theta is approximately theta. If we do that, then f sine theta equals mu theta c squared becomes f theta equals mu theta c squared. The thetas cancel, so c is square root f over mu. So that's the speed of the wave in that string. So, or a rope or whatever. So this thing is moving along, and so it's moving at some speed. C square root f over mu. So that means that if it's under higher tension, it goes faster. And if the rope is a lighter, less mass per length, then it's going to go faster. So in other words, I can think of a guitar string. You have the guitar string, and you can have another guitar string that's thicker, okay? And so if you pluck both guitar strings, then the thicker guitar string has more mass per length in it. And so that means a wave goes slower on the thicker guitar string than it does on the narrower guitar string. Well, also, the thing is, the narrower guitar string, thicker guitar string, you can change the tension. So you could actually increase the tension on the thicker one, and that would make it go faster. And so it is possible to actually play the same note on 2 different guitar strings if there are different thicknesses, if the tensions are different, or sufficiently different. And so all this plays into speed of waves. And so what I normally do about this point is I demonstrate this in class and have a student stand on one side of the class, and I have a long spring or something that stretches across the entire class, and I start shaking it and sending waves down it, and I change the tension and they go different speeds, and then I change to a different thing. I'm sending the waves down and they go different speeds. Now we can't really do that, but I did find a video of someone else that did that on YouTube in a class. So I'm gonna the next topic is gonna be a link to that video, and so that'll be what you'll watch next. Is what a demo I would have done myself in class.